videos with your name and town to the One Africa TV's WhatsApp on 081 200 6659 or send an SMS to 555. One Africa TV, it just gets better.
Enjoy these fantastic payday savings at Clicks until 6 August. Buy Yardley body spray for women 90 mils, 2 for $54. Buy Pampers baby dry disposable nappies jumbo packs, now 2 $25.99 per pack. And buy Nivea lotion or cream 400 mils, 2 for $75. Buy Omo auto washing powder 2 kgs, 2 for $102. Clicks, feel good, pay less.
Example 1 asks, are the following triangles congruent? So we have two triangles, each with two angles of 15 degrees and 115 degrees, and both have sides of 4 centimeters. If we look at both of these triangles, we can see, as I had said before, that we have two angles of equal magnitude. Both triangles have a 115 degree angle, and both have a 15 degree angle. Also, both triangles have a side of length 4 centimeters. If we think back to the previous lecture, we may be considering the angle-angle side condition to prove congruency. But there is a trick in this question. If you look at the first triangle, you will see that the 4 centimeter side is opposite the 50 degree angle in the triangle. And if you look in the second triangle, the 4 centimeter side is opposite the 15 degree angle. Because of the fact that the 4 centimeter side is opposite different angles in those two triangles, the triangles are not congruent. Example 2 is in fact a routine problem. We have two triangles, each with a side of 8 centimeters and 16 centimeters and a 90 degree angle. We are asked to prove whether these triangles are congruent or not. So, we're going to consider triangle ABC, and we're going to consider triangle XYZ. In triangle ABC, we can see that angle B is a 90 degree angle, and in triangle XYZ, angle Y is the 90 degree angle. So we have a right angle. Now, if we look at triangle ABC, side AC, which is the hypotenuse, is equal to 16 centimeters. And for the other triangle, side ZX is equal to 16 centimeters, which is also the hypotenuse. So we can see that the hypotenuse of both triangles is equal in magnitude. Finally, if we look at triangle ABC, we can see that BC is equal to 8 centimeters, and in triangle XYZ, YX is equal to 8 centimeters. We have an additional side in both triangles that is equal in magnitude. Therefore, by the right angle hypotenuse side condition of congruency, we can see that triangle ABC is congruent to triangle ZYX. Please note, the triangles above are in fact the same shape and size. If one of the triangles was reorientated, it would easily be seen that they are in fact the same triangle. Given the following diagram, we have to prove that triangle XYZ is congruent to triangle XDZ. So, let's begin. If we look at our diagram, we can see that angle O1 is equal to angle O2, and both of these angles are actually 90 degrees. And this has simply been given to us. So immediately we have an angle. Furthermore, we know that side DO is equal to side YO in magnitude. This has also been given, so we have a given side. And last but not least, we know that XO is a common side of the triangle, which means that for triangle XOY and XOD, XO is obviously the same in magnitude. Also, if you look at angles O1 and O2, they are actually included angles. So, by the side angle side condition, triangle XOY is congruent to triangle XOD. Please note, the reason we use the side angle side condition is because the 90-degree angle in both of those triangles is the included angle. That is, it is the angle between the two sides. By congruency of triangle XOY and triangle XOD, we know further things. Angle Y1 is equal to angle D1, which obviously implies that angle Y as a whole is equal to angle D as a whole, since angle Y2 is equal to angle D2, and this has also been given to us. Also, by the congruency of triangle XOY and triangle XOD, we know that the magnitude of side XY is equal to the magnitude of the side XD. Therefore, we have the following. Angle Y is equal to angle D, which is our angle. Side XY is equal to side XD, which is our side. We also know that the length of the side YZ is equal to the length of the side DZ because we have equal angles opposite equal sides, because angle Y2 is equal to angle D2. So we have another side. Therefore, by side angle side, triangle XYZ is congruent to triangle XDZ. Please be aware of the fact that if you came up with another solution that was mathematically valid, you would be awarded all credit.
It is very important to always put all the given information of a geometry question on the diagram. So in this question, being example 4, we are given that O is the center of the circle. There is O at the center. We are also told that M is the midpoint of the chord AB. Therefore, AM would equal MB. We are asked to prove that OM bisects the angle AOB. In other words, the line OM there bisects, meaning cuts in half, AOB. In other words, angle O1 must end up being equal to angle O2. Well, how are we going to prove this? Well, to start with, we know that since O is the center of the circle, line AO and line OB must be equal. Why? Well, if you look closely, you'll notice that both of them are radii. We also have been given that AM equals MB, and we know that OM is a common side between triangle OAM and OMB. So let's write this down in a formal proof. To start off, we must always name the triangles. Therefore, in triangle OAM and triangle OBM, and now we must write down our 3 reasons for congruency. First of all, we know that AM equals MB, and our reason is given. It was given in our initial blurb. The second reason for congruency is that OA equals OB. That reason is going to be radii, because OA is a radius of your circle and OB is a radius of your circle. And the third reason is going to be OM equals OM. The reason for that, however, is common. It is a common side. Now that we have three reasons, we can have our final statement. Therefore, triangle OAM is congruent, the three horizontal lines, to triangle OBM, and my reason of congruency will be side, side, side.
In this lesson, we will look at the different types of triangles, and we will also look at the properties of these triangles. To begin, we will look at the different types of triangles in geometry. Triangles are either right-angled, that is, one angle within the triangle is 90 degrees, or triangles are oblique, that is, no angles within the triangles are 90-degree angles. In diagram A, triangle ABC is a right-angled triangle. It can be seen that the right angle, or the 90-degree angle, is angle B. Moreover, the side AC of triangle ABC is opposite the right angle, and it is this side in the right-angled triangle which we call the hypotenuse. The hypotenuse is the longest side of a right-angled triangle. As will be seen in another lesson, the right angle of a triangle will be a prerequisite when applying the Pythagorean theorem. In diagram B, triangle ABC is called an oblique triangle since neither angle A, nor B, nor C is a 90-degree angle. Now, there are three main types of triangles. They are, number one, the equilateral triangle. The magnitudes of the angles within and the magnitudes of the sides of an equilateral triangle are all equal. This means that angle X is equal to angle Y, which is equal to angle Z, which is equal to 60 degrees, and side XZ is equal to side ZY, which is equal to side XY. Since all the angles within an equilateral triangle are 60 degrees, it is evident that all equilateral triangles are oblique triangles. Number two, the isosceles triangle. The isosceles triangle will have two angles within it of equal magnitudes. Consequently, the magnitudes of the sides of the triangle opposite these angles will also be equal. In the diagram, we can see that triangle XYZ is isosceles since angle X is equal to angle Y, and so side XZ is equal to side ZY. Moreover, an isosceles triangle may be right-angled or oblique. And finally, number three, we have the scalene triangle. The scalene triangle has no angles or sides of equal magnitude. Referring to the diagram, this means that angle X is not equal to angle Y, which is not equal to angle Z, and side XZ is not equal to side ZY, which is not equal to side XY. Scalene triangles may be oblique or right-angled. Example 1. Example 1 says, given the following diagram, classify the type of triangle with justifications. So, we have triangle DEF, where angle D is equal to 120 degrees, angle E is equal to 35 degrees, and angle F is equal to 25 degrees. Please note that the triangle that has been given is not drawn to scale. So, since angle D is equal to 120 degrees, angle E is equal to 35 degrees, and angle F is equal to 25 degrees, which are not 90-degree angles, it is obvious that triangle DEF is an oblique triangle. Additionally, triangle DEF is a scalene triangle, and consequently the magnitudes of side DE, side EF, and side FD will not be equal. We now move on to example 2. Example 2 says, an isosceles triangle can be either oblique or right angled. Validate this claim with 2 examples. To begin the solution to this question, we must first recall the definition of an isosceles triangle. Well, we know that an isosceles triangle has 2 angles of equal magnitude where the sides opposite these angles are also equal in size. Let us consider now triangle ABC. We will let triangle ABC be such that angle A is equal to angle B. Furthermore, the magnitudes of the sides is arbitrary, but we know that AC is equal to BC. We first want to generate a right-angled triangle ABC. So we let angle C be equal to 90 degrees. Since angle A is equal to angle B and all angles in a triangle must sum to 180 degrees. So angle A plus angle B plus angle C is equal to 180 degrees. This implies that angle A plus angle B plus 90 degrees is equal to 180 degrees. This implies that 2 times angle A is equal to 90 degrees, which implies that angle A is equal to 45 degrees. Hence, angle B is also equal to 45 degrees. This means that triangle ABC is both right-angled and isosceles if angle A is equal to angle B, which is equal to 45 degrees, and angle C is equal to 90 degrees. Now, to generate an oblique isosceles triangle, we will now make sure that angle C is not equal to 90 degrees. So, we will let angle C equal, let's say, 80 degrees. Since angle A is equal to angle B and all the angles within a triangle must sum to 180 degrees, we know that angle A plus angle B plus angle C is equal to 180 degrees, which implies that angle A plus angle B plus 80 degrees is equal to 180 degrees. This then implies that 2 times angle A is equal to 100 degrees, which then implies that angle A is equal to 50 degrees, and hence angle B is equal to 50 degrees. This means that triangle ABC is both oblique and isosceles if angle A is equal to angle B, which is equal to 50 degrees, and angle C is equal to 80 degrees. We will now look at the properties of triangles. There are 2 important properties that must be understood when dealing with triangles. They are: Property 1. Property 1 says that all angles within a triangle must sum to 180 degrees. So, if we consider triangle ABC, then angle A plus angle B plus angle C must equal 180 degrees. Property 2. Property 2 says that the magnitude of the exterior angle of a triangle is the sum of the 2 opposite interior angles' magnitudes. So, if we consider triangle XYZ, then angle X plus angle Y is equal to angle W. This now leads us to example 3. Example 3 says, given the following diagram, find the value of f. Now, there are 2 ways to approach this question. Approach 1. We know that G is equal to 180 degrees minus 110 degrees, which is equal to 70 degrees, since all the angles on a straight line add up to 180 degrees. Therefore, angle F is equal to 180 degrees minus 20 degrees minus 70 degrees, which is equal to 90 degrees. And this is because the sum of the angles in a triangle is 180 degrees. Hence, angle F quite simply is equal to 90 degrees. Now we look at approach 2. We know that angle E plus angle F is equal to 110 degrees because the sum of the opposite interior angles within a triangle equals the exterior angle of that triangle. This implies that 20 degrees plus F is equal to 110 degrees because it has been given that angle E is equal to 20 degrees. This implies then that F is equal to 110 degrees minus 20 degrees, which is equal to 90 degrees. Hence, angle F is equal to 90 degrees. Thus, triangle EFG is a right-angled triangle. We now look at our final example, example 4. Example 4 says, determine the value of h corresponding to the following diagram. Well, we know that I is equal to j. This is because we have equal angles opposite equal sides. In other words, the triangle that we are dealing with is an isosceles triangle. Therefore, 29 degrees plus I plus j is equal to 180 degrees because the sum of all angles in a triangle is 180 degrees. This then means that 29 degrees plus 2I is equal to 180 degrees because angle I is equal to angle j. Hence, 2I is equal to 151 degrees, which implies then that I is equal to 75.5 degrees. Hence, I is equal to j, which is equal to 75.5 degrees. Now, we know that h is equal to 29 degrees plus j, because the sum of the opposite interior angles in a triangle equal the exterior angle of a triangle. Hence, h is equal to 29 degrees plus 75.5 degrees, which then means that h is equal to 104.5 degrees.
What is surface area? Surface area is the total combined area of all the surfaces or faces of a three-dimensional object or shape. As with the area of any 2D shape, surface area is also measured in square units. For example, square millimeters, square centimeters, square meters, or square kilometers. To understand this better, let's look at a square. The area of a rectangle or square can be worked out when we take the length, in this example 4 units, and multiply it by the breadth, which in this instance is also 4. This would give us an area of 16 square units. Linking this idea to a three-dimensional shape, we will look at a cube. A cube is a 3D shape or object made up of faces that are all squares. If we were to unpack the cube into a net, this would form a 2D shape made of faces. So, to work out the surface area of the cube, we need to work out the area of each of the individual faces and then add them together. In this instance, each face is 16 square units and we have 6 faces. This would give us a total surface area of 96 square units. The same approach can be used to find the surface area of any 3D shape or object, even the ones which seem to be complicated.
Hello and welcome to this week's IGCSE International GCSE Maths Core live lesson. It's a beautiful Friday. It's Valentine's Day, so let's have an awesome session and learn a lot about prime numbers. Okay, so let's have a quick look. Last week we did cover a little bit about factorization and multiples, factors and multiples. And I started to look a little bit at prime factorization or prime factor ladders. So I'd like to just expand a little bit about that, a little bit on that today, and speak about how to use prime factor ladders, how really important they are in understanding numbers, and using them to look at HCF, LCM, and if we have time at the end, to look at cube and square roots. Okay, so let's jump in. Today we're doing International GCSE Core Maths. We're on week 2, prime factorization, HCF and LCM, if you're following on your Cambridge Learn platform. Okay, so let's talk about prime factorization and what factor ladders are. So we know that any number can be written as a product of its prime factors. Okay, so we can multiply prime numbers together, and when we multiply prime numbers together in a certain way, we can find any number's product. So let's try the first one. Let's try, for example, something quite simple. Let's try the number 24. Okay, and so last week we looked at prime factor ladders, noting what a prime number is. So prime means a number that has two factors. And these factors are 1 and itself. So any number that only has two factors, it has two factors and only two factors. So for example, 1 is not a prime number because it only has one factor, which is 1. And so 1 is not a prime number. Okay, so the first prime number is 2. 2 is the first prime number. It's also the only even prime number. And so if I divide 24 by 2, and I put my prime numbers here, put my primes over here. Okay. If I divide 24 by 2, I'm going to get 12. And then I look at 12 and I say, okay, well, what's the first prime number that can go into 12? Well, it's also 2. Okay, and if I divide 12 by 2, I get 6. And then I look at 6 and I say, okay, well, the first prime number that can go into 6 is also 2. Okay, and I get, if I divide 2 into 6, I get 3. As I go, I'm going to create the rungs of my ladder. And if I want to divide 3 by a prime number, well, I have to divide it by 3. 3 is the only prime number that will go into 3 because 3 is prime itself. And I'm going to be left with 1. And when I'm left with 1 over here, I am done. All right. Cool. So if we want to write a number as a product of its prime factors, I will write it in terms of these numbers multiplied together. So for example, I'm going to say 24 is equal to 2 times 2 times 2 times 3, or 2 cubed times 3. And this just means times by itself 3 times. And if I calculate this, 2 times 2 is 4, times 2 is 8, so 2 cubed is 8, and 8 times 3 is 24. So I know that I am correct. So this is how I write something as a product of a prime factor. And I must say the number is equal to the prime factors that make it up. Okay, so that is a factor ladder as well as prime factorization. Okay, so when we say write a number as a product of its prime factors or use prime factorizations to find, we will use a factor ladder, or we can use a calculated trick, which I'll show you at the end. But it's important to understand that we must be able to do the prime factor ladder in case something is worth more than 1 mark. So when we have something that might be worth, let's say, maybe 4 marks, we know that if we are involving prime factors, we use a prime factor ladder and we do the complete statement and to get all of our marks. Okay.
Share with us on #LearnOn1. Tell us what you're learning and where you're learning it from. Send us your name and town to the One Africa TV's WhatsApp